Today we're going to switch gears and talk about derivatives. We've been talking about limits, which is the first calculus topic. Now we're going to talk about derivatives, which is the second calculus topic. And we're going to start with just an overview of what a derivative is. So when we talk about a derivative, we're talking about how a function is changing. We specifically call it a rate of change. Okay, so a derivative describes a rate of change of a function. And so you're familiar with the terminology rate of change when you talk about the slope of a line. When you're talking about the slope, you're also talking about the rate of change. So analytically, we have what's called the definition of a derivative, or it's also called a difference quotient. And this is the definition of the derivative. And the definition of a derivative actually gives you the slope of the secant line. And so if I'm trying to find the slope at a particular point, that's what a derivative is. But when you're estimating it, you start by finding the slope of a secant. And then you let this distance here between the 2 points get smaller and smaller and smaller and smaller until eventually you're just looking at the slope of the tangent line. And so this formula here is talking about the limit as h approaches 0. Well, h is the difference here between x and x plus h. That's this distance between the 2 points. So as this h gets infinitely small, heading towards 0, this formula, f of x plus h, that's this point here, the y value, minus f of x, that's the y value of the starting point, all divided by the h, that's the difference in the x's. What we have is delta y minus delta y over delta x. Come back here. Delta y over delta x. And so that's your slope formula. And so this limit formula that talks about the rate of change is basically just your slope formula. You need to know this difference quotient. It's called the difference quotient or the definition of a derivative. You need to have that formula memorized. Put a big star out beside that. You need to have this memorized. You're going to use that a lot. So when we talk about analyzing the slope of an equation, graphically, the derivative at a particular point is the slope of the tangent line at that point. So if we're trying to find the slope at this point, we want the slope of the tangent line. So rise over run, difference in the y over the difference in the x is your slope formula. And you will spend a lot of time finding slopes of tangent lines. So here are the different most common notations that indicate a derivative. So if your function is named f of x, the derivative would be called f prime of x. That little apostrophe is called prime. If your function is named y, then your derivative is y prime. We talk about a derivative as being dy over dx. That's the difference in the y's over the difference in the x's, which you know is your slope formula. So that's a very common notation. And then this notation here means the derivative of f of x. So those are the most common notations that you will see in calculus when you're talking about derivatives of functions. So just make sure that you're familiar with those. If you see them, you know what they mean. Okay, so on these first several problems, what we're doing is using that definition of a derivative formula. So we need to write it down. The slope is equal to f of x plus h minus f of x. And I already messed it up. All right, let's go back again. The slope is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. we're going to use that formula, which is called the definition of a derivative, to find an expression for the slope of the line tangent to the graph of the given function. So what we're going to end up with is another equation. Okay, and it's going to be the equation that represents the derivative at whatever point you want to calculate. So, starting with the formula, what I'm wanting to do when I'm finding f of x plus h is take this whole equation, and in place of the x's, I'm going to substitute an x plus h. So m is equal to x plus h squared minus 2 times x plus h plus 3. Okay, so all of that is your f of x plus h. Then I want to subtract from it f of x. So subtract from it f of x, which is x squared minus 2x plus 3. Notice I put that in parentheses because I'm going to need to distribute my negative sign so that I'm subtracting all the terms. Put all of that over h and then add the limit in front, the limit as h approaches 0. Okay, so if you remember when we're evaluating limits, the first thing we always try to do is to plug in the value that your variable is approaching. So h is approaching 0. So if I were to plug in a 0 for all the h's, notice in the denominator what would happen. I would end up with a 0 in the denominator, which I can't have. So that means, being as this is a rational function with the numerator and denominator, that I need to do some manipulating to try to factor or get it factored or something so that I can cancel that h. So I'm going to go through and I'm going to FOIL this, distribute that, combine like terms, and see what I can do to simplify. So x plus h squared is x squared plus 2xh plus h squared. Distribute the negative 2, it's a negative 2x minus 2h plus 3. And then I need to subtract all of this, so minus x squared plus 2x minus 3. All of this is still over h. Yes, it's a lot of terms, but watch what's going to happen now. I'm going to go through and cancel anything in the numerator that adds up to 0. So an x squared and a negative x squared. A negative 2x and a positive 2x. Positive 3 and a negative 3. Look how everything starts canceling, which is what's going to happen every time. It's always going to work like this. So now rewrite the limit as h approaches 0 of 2xh plus h squared minus 2h all over h. And then the next step is to notice that each of these terms in the numerator has an h in it. So if I could factor out the h, then I could cancel with the h in the denominator. So the limit as h approaches 0, taking out an h, I get 2x plus h minus 2 all over h. So these h's here will cancel. Limit as h approaches 0 now of what's left over, 2x plus h minus 2. And now I'm going to plug the 0 in. So plugging a 0 in just for the h, I get 2x plus 0 minus 2, which is 2x minus 2. That is an expression that you can use to calculate the slope of the tangent line to this equation at whatever point you want to plug into the x value. Okay, so that's the equation of the slope of the tangent line. You have to be able to work through this whole process using this formula in order to come up with these equations. And then, once you're good at this, we'll learn some shorter ways to go about the process. But for right now, you need to understand how to use this formula. So let's look at it with this next one. We've got y equals the square root of 2x plus 3. So our formula again The slope is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Alright, so when I want f of x plus h, that's going to be the square root of 2 times x plus h plus 3. So m is equal to the limit as h approaches 0 of the square root of 2 times x plus h plus 3. It's all under the radical. That's your f of x plus h. Subtract from it f of x, which is just the square root of 2x plus 3, which is all over h. Now, if we were to plug the 0 in for h, that's our first thing to try. We would end up with a 0 in the denominator, so that's not going to work. So we want to manipulate it, and this is the example where the conjugate would be the way to go because we've got radicals, so I want to multiply by the conjugate, which would be the square root of 2 times x plus h plus 3 plus the square root of 2x plus 3 on top and bottom. Okay, remember what you've been told previously about leaving this in factored form. We want to go ahead and FOIL the numerator, but being conjugates means that I don't have to do the inside and the outside, just the first times first and last times last. So the limit as h approaches 0 for the numerator. Remember, radical times radical just makes the radical cancel. First times first, last times last. Leave the denominator in factored form. Alright, so now let's do some simplifying in the numerator. The limit as h approaches 0, I'm going to distribute the 2 and get a 2x plus 2h plus 3 minus 2x minus 3. Leave the denominator in factored form. Alright, so let's group all of our like terms that are going to cancel, a 2x and a negative 2x, 3 and a negative 3. Remember I said that that would always happen that way. And now what's left, the only thing we have left in the numerator is a 2 times h. So I can now cancel this h with that h that we left factored out and rewrite my limit statement. So I've got a 2 in the numerator. I've got a 2 times x plus h plus 3 under the radical plus under a radical 2x plus 3. Our h canceled. Now we're ready to plug the 0 in. So plugging 0 into this h here, I get 2 over the square root of 2x plus 3 plus the square root of 2x plus 3. I plug the 0 in for the h. So in the denominator, I've got two radicals that match. I can add them together, and I get 2 times the radical, 2x plus 3. And now these 2's cancel, and I'm left with 1 over the square root of 2x plus 3. And that is an expression that you can use to find the slope of a tangent line to this equation right here at whatever x value you want to plug into it. So those examples were assuming that you just wanted a general formula to find the tangent. If you know that you want to find the slope of the tangent at a particular point, there's an alternate version of this difference quotient formula that we can use if we know the point that we are wanting to find the derivative at. In other words, the a. And so it looks the same, except for instead of an x, we have an a. So let's work through this next example that says, use the alternate form of the definition of a derivative to find the slope of the line tangent to the given graph at a specific point. And so at a specific x value. So scoop this up. The only difference is instead of having an x in your formula, you're going to have the x value from the point. So m is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay, so a is 2. That's the x value that we're finding it at. So I'm going to go ahead and plug in a 2 plus h into this. So 2 plus h squared plus 1. That's the a plus h, f at a plus h, minus f at a. So 2 squared plus 1. That's f at 2 with f at a all over h. Okay, so I'm going to do some cleaning up, rewrite it. The limit as h approaches 0. I'm going to FOIL this. 2 plus h squared is 4 plus 4h plus h squared plus 1. Then minus 2 squared plus 1 is 5, so minus 5 all over h. Notice that we don't have all these x's all over the place this time. So it makes it easier to work with if you go ahead and plug that 2 in place of the x. All right, so let's see what we can cancel. We said that there would be values that would cancel. Here's a 4 plus a 1 is 5 minus 5. Those cancel, which leaves us with the limit as h approaches 0 of 4h plus h squared over h. Now if we could just factor an h out of those two terms in the numerator, we could cancel it with the denominator. So the limit as h approaches 0, factor out the h and get 4 plus h, which allows you to cancel these h's, leaving me with the limit as h approaches 0 of 4 plus h. And now we can plug the 0 in for our h and get 4 plus 0 or 4. So the slope of the tangent line at this particular point is equal to 4. Now that doesn't help you if you want a general formula that you could use for any point, but if all you care about is the slope at one specific point, then that's easier to work through the math. All right, let's look at one more example. We're still finding the slope at a specific point, so we still want to use our new version. M is equal to the limit as h approaches 0 of f of a plus h minus f at a all over h. Okay, so if this is my equation, then f at a plus h is 1 over a plus h. In this case, the a is your x value, so we're going to plug in a 2 for that. So the limit as h approaches 0 of 1 over 2 plus h minus 1 over 2 all divided by h. Okay, so once again, if I were to plug the 0 in at this point, I would get the 0 in the denominator, 0 in the numerator, so we need to manipulate. We've got fractions on top, so we want to combine those together, get a common denominator. So the common denominator would be 2 times 2 plus h. The numerator, I would multiply this one times 2 over 2, the second one by 2 plus h over 2 plus h. And so that would give me 2 minus 2 plus h. Okay, rewrite it so that I've got stuff simplified. So 2 minus h over 2 times 2 plus h. And then instead of divided by, I'm going to multiply it by 1 over h. All right, 2 minus 2. Those are gone. So I've got the limit as h approaches 0 of negative h over 2 times 2 plus h, all that times h. Oops, this was a negative h, my bad. Negative h on top. So you see that we've got h's that will cancel. I'm left with a negative 1 on top. And I've got a 2 times 2 plus h in the denominator. So at this point, we can go ahead and plug the 0 in for the h. I've got negative 1 in the numerator. 2 times 2 plus 0 is negative 1/4. So that would be the slope of this equation, the tangent to this equation, at this particular point.